Today we're going to go in and talk about selected vibrational modes. It's often useful to consider a particular kind of vibrational mode. So we just learned how to find all of the vibrational modes and then to select which ones were IR active and Raman active. But what if you just want to know about one type of vibrational mode? So we're going to look at CO bonds. What I just said, it's often useful to consider a particular kind of vibrational mode for a compound. So we're going to use the example of CO stretching bands because this is a pretty practical thing. The CO bands often give useful structural information. So I'm going to give you an example of two molecules. Let's say you just were in lab and you synthesized some compound that had that. So you knew the molecular formula was platinum CO2 CO, two of those. So you know that's the molecular formula. But you don't know if you have the trans isomer or the cis isomer. So we can assume that we have either the trans or the cis isomer. But we don't know which one. What we can do is we can determine how many vibrational stretches we would see in the IR, the Raman spectrum, from just the carbonyls or the carbon monoxide. So to find those CO stretches, you just treat the COs as its own set. So you look at a vector along the CO stretching axis or the CO bond axis, so that vector or this vector, and when you make the reducible representation, that's the only thing that you're going to look at are those vectors. So just like any time when you're trying to find vibrational modes, what's the first thing that you have to do? The first thing I always do when I'm dealing with a new molecule. Yeah, you have to assign the point group. So what are the point groups for these molecules? Are you looking at the trans or the cis? Trans. Okay, the trans. Let's see. I'm going to write my axes in green. So there's a C2 axis where? In the plane of the molecule somewhere, right? Yeah. So there's a C2 axis that actually goes this way, there's a C2 axis that goes this way, and then there's a C2 axis that's there. Wait, is that right? Nope, there's not one. Nope. So there's two C2 axes. So whatever, we found C2. There's not a C4 in this molecule, right? So C2 is our highest order axis. So let's just pick one of these two C2 axes and ask, is there a horizontal mirror plane? So if I pick this one, okay, that's my C2. Is there a horizontal mirror plane? Yes. D2H. Okay, so my cis molecule, what do you think? What's the highest order rotation axis? C. Do you see? No, I don't see a 4. D2 there, right? Is there a horizontal mirror plane? No. So, what is it? Yes, because there's a vertical mirror plane. And I'm jumping ahead. You know what? The second question you ask yourself after you find the rotation axis is there a perpendicular C2, not a horizontal mirror plane? Sorry, I'm skipping. So this one had a perpendicular C2, and we found it there. But this one over here did not. Okay, so we have D2H and C2V. So which one do you want to do first? Those are trans. Trans? Okay. So we're going to look at the trans molecule, and I'm just going to abbreviate M with, the platinum with M, L, and L. Okay. So now we're going to do under the D2H point group. So D2H, if you look in your character table, you will see these symmetry elements. So now we need to make a reducible representation of the carbon-oxygen bonds. So for E, what's my number? Just for the carbons? Yeah. So it's actually for the vectors along the carbon-oxygen bond. but you're right, it is 2. What about for C2Z? Okay, I guess right now we should probably define our axes. So let's define, it's probably best if we define the axes in the, let's see, there's a C2 there, a C2 there, not one there. So I think we should do this. Let's do Z, X, and then Y is going to come out. And I'm going to define the axes along the bond. Do you see what I'm doing? Or do I need to rotate my molecule to make it clear? Okay, let me erase this and I'll change it. So I'll do Z, X, and Y, and I'll have metal CO, CO, L, L. There. Okay? So, if we rotate along the Z-axis, how many of the carbonyls stay the same? You're right, both of them. So, what's their number here? 2. What if we rotate along the Y-axis? What's our number? It is 0, you're correct. And along the X-axis? 0. Inversion? 0. Sigma XY. So basically, a reflection through the ligands. 0. Sigma XZ. So in the plane of the molecule. And YZ? So along the CO bonds? 2. Good. Okay. So then what do we do when we have a reducible representation? Break it up into irreducibles. So I will tell you that you have an AG, which is the most symmetric, would be 1s all across the board, and then you could probably tell just by adding up numbers what the next one would be, and you'd find it was a B1U. That's when you use the formula that I gave you last time. The one where you multiply the number, so you have to go to the character table and look at all of the irreducible representations, and then you take the number of characters in the class, okay, multiply that by the number of the reducible representation, and then you multiply it by the number of the irreducible representation. You add those all up, divide by the order of the group, and that tells you how many of each type. Okay, so go back and look at your notes from Wednesday.
How do you know it's AG?
Because,
Are you just looking at the...
yes. So you have to look at the character table. So there's 2 ways to do it. One is by inspection. And that's when you look at the character table. So for really simple ones, so when this number here is low, it's really easy to do this after you get used to it. When that number is like more than 3, or if I have a really symmetric group that has a whole bunch of irreducible representations, that's when I say, screw it, I'm going to do the formula because I know that I'm not going to figure this out by just looking at the character table. But for this one, it's really easy. You always start with the most symmetric. So basically the first line in the character table always has 1. So if you go back and you look at the formula for how you figured this out, you'll hopefully understand why when you basically you're adding all across, so you have to come up with a positive number. So you'll always have at least one of those the most symmetric irreducible representation. So you'll always have at least one of those. So I usually just start by putting one of these on there, labeling it. Okay, in this character or in this point group, it's AG.
But how is it AG? That's where I'm at.
Okay, let's go to the D2H character table. So this is a photocopy of the textbook character table. So what do I want? D2H. There it is. Okay. Can you see that? That's my character. This is the D2H character table. So I see that the top line here, which has all positive numbers, that's AG. So
it's always the top.
yeah, it's always the top one because they put the most symmetric at the top. So remember what these characters mean is that the whatever this is, it doesn't change with each operation. So that's like the most symmetric irreducible representation. So you'll always have one of those. Well, so if I was in D3H, I would have an A1 prime, probably. Okay? So when it's a really small number in your, oops, that's organic. Where's my inorganic? There we go. When you have a really small number up here, like 2 or 3, when you just start by writing this guy here and then seeing how the number, so if I didn't know this was B1U, all I have to do is say, okay, well, 1 plus what is 2? 1. 1 plus what is 2? 1. 1 plus what is 0? -1. So I just go across the whole thing like that, and then I go find what matches this. So this is 1, 1, and then all negative ones until the last 2, and then I have 1s again. So I look back at my character table. Okay, so I have positive 1s. Obviously, it's not going to be the first one, so I have 2 positive 1s, and then negative, negative, positive, positive. Okay, it's not that one. See. Okay, here's 2 negatives. Oh, no. Oh, here it is. Positive, positive, negative, 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 and then positive, positive. So I have a B1U. That's what I wrote. Okay. All right. Does that make more sense? Okay. No problem. So now I want to know, I have my irreducible representations, and this tells me the symmetries of the vibrations. Now I want to know, where are they IR active, are they Raman active, or neither? So I want to go to my character table again and look for what? So if I'm looking for IR active modes, I'm looking for what? X, Y, or Z. So let's go to our character table. So for AG, what do I have over here? These are not Raman active, or sorry, these are not IR active, but they are Raman active, right? So my AG is Raman active, but not IR active. And then my B1U is IR active, but not Raman active. So this one had Z in the character table. This one had X squared, Y squared, and Z squared. So this A1, or sorry, the AG is Raman active, and the B1U is IR active. So for and I'm talking again about not just all the vibrations that I would see, but specifically the ones that would come in the region of a carbon-oxygen stretch. So I can look in the region of my IR spectrum and look for how many carbon-oxygen stretches do I have. So for this molecule, for the trans, I can expect 1 IR stretch. And I can also expect 1 Raman stretch, but I'm just going to look at the IR spectrum because it's easier, and we don't have a Raman at this school, so I'd have to go over to Notre Dame. So now let's look at the cis isomer. How many IR stretches do I have there? So I'm looking at the vector on the carbon-oxygen bond, and I have a C2V point group, and if I look at my character table, I can see that the characters are E, C2, sigma V, and sigma V prime. So this is the same one that we were using for water. So C2V. So the sigma V is in the XZ, sigma V prime is the YZ. You know what I'm going to do is I'm going to rotate my molecule so that the C2 axis, can I do that? No, it doesn't let me rotate. Let's see. I'll just erase it. I want to put my C2 axis in the Z direction and make my axes convenient. So I'll just go with the same axis system, and I'll write it like this. CO, CO, L, L. So now my Z axis is pointed up. So that's my principal axis. Okay, so now what is my reducible representation for those carbon-oxygen bonds? What's E? Yep. All right, I'm going to write them here, and I want you to tell me if you agree. Okay? So, again, I'm dealing with a tiny number, number 2. So I'm just going to write, okay, I know that I probably have one of my symmetric, the most symmetric in the character table, and so then my next my irreducible representation would be 1, -1, 1, -1, and then I can just go to the character table and see what those look like. And go to the character, so that's A1 and B1. And then I want to go and I want to see what those match up with. So A1, is it Raman active? It's the top character table up here. It's A1 Raman active. Is it IR active? Good. What about B1? Is it IR active? Is it Raman active? Just for fun? Ooh, yeah, it is. So it doesn't have to be x squared, y squared, or z squared. It just has to be a product of 2 of the vectors. So these 3 here count. So those would be Raman active. So, oops. Okay, so this A1 transformed as Z, B1 transformed as X. So those are, in fact, IR active. And so in this spectrum, we would expect 2 IR stretches. And if we wanted to look at the Raman, both of them are also Raman active. So if I told you that there was one band, the data, when you take the spectrum of this product, shows 2 IR bands. So it cannot be the trans isomer. It can only be the cis isomer because you get 2 IR bands. However, remember that this is just data. You're the one that's interpreting it. So it's still possible, if you have 2 IR stretches, it's still possible that you might have the 2 different isomers and they, are giving you 2 separate bands. If I only had 1 IR stretch, I still could not exclude the cis isomer because the 2 stretches can overlap in your actual spectrum. So you have to keep that information in mind if you're doing this in real life. But it tells you what you can expect. So, I figured you guys would want some more practice, and so we're going to do this activity. So I handed you all a piece of paper that says IR spectroscopy, predicting the structures of rhodium carbonyl clusters. You have a problem from this on your homework. Okay, so problem set 4, which is due on Friday before you get to take the exam. Okay, and that's for your own good, so that you do it, because these will be on the exam. Okay, so that doesn't motivate you, I don't know what will. I want you to read the instructions. In short, we're going to be looking at the carbonyl, or the carbon-oxygen stretches, but in these molecules, there are 2 different types. There are terminal CO stretches, and there are also bridging COs. So in the bridging COs, you're going to treat those as different than the terminal COs. So I want you to look at them and tell me how many stretches that you would expect from each type of CO. The first thing we have to do is assign point groups.